Well, in the name of God, I'm going to start by welcoming you back to this series of lectures or tutorials on kinetic theory of gases. Already we've got 4 videos. The first one was an introduction. The second one was about some revision concerning probability, what it means. The third video was about probability density. We've seen some examples of probability density functions, and some integration formulas related to that. Video number 4, we've talked about statistical definition of temperature, where we have seen that actually what temperature means can be taken from this formula that 1 divided by Kb. T is the temperature here, so this left-hand side, Kb is Boltzmann constant. We've derived that this is actually differentiation. You differentiate logarithm of omega function of E. Omega is number of states, number of microstates of the system under consideration as a function of energy. So how does that change? If you differentiate that with respect to energy, you can get what we call temperature. Okay? Today we're going to build on that result into the next topic, number 5, which is going to be about Boltzmann distribution. So it's going to build on what we've done already, and at the end of the day we're going to have some probability distribution, which is named after Boltzmann. Given an energy for a thermal system, one would be able to have a probability measure which is depending on the energy. Okay. We begin with some definitions. So let me pick a different color. Definitions. And the first one is the word ensemble. So maybe that, what does an ensemble mean? A large copies of a system is called ensemble. So a thermal system can have different states, physical states, thermal states, and the state of the systems are usually labeled by macroscopic variables. So an example is temperature, another example is energy, right? So you can have a system at a particular macroscopic state having a particular energy, right? And one can think of various or many large number of copies of a given system. This is what is called an ensemble. So we write here large number of mental copies of a system, each one representing a possible state. So here there is a mention of being the copies are mental, so it's not necessary for it to be real. One can make an ensemble, for example, in a simulation, so that is also not real. But one can consider such sample, okay, of a system representing different possible states of the system. So this is what we call an ensemble. Another word that maybe we're going to come across is microcanonical ensemble. Microcanonical ensemble. So this is an ensemble of different states with a fixed energy, right? So energy is fixed, it's not allowed to vary. An ensemble of different states. Each having the same fixed energy. And the third definition is canonical ensemble. So this is also ensemble. Oh. This is an ensemble of different states, each in thermal contact with a large reservoir. Okay, so here, in some sense, there may be change in energy. The energy can vary because the system under consideration is in contact with a reservoir. So this is an ensemble of different states, each in thermal contact, therefore can exchange energy with a large reservoir. Of heat. This large reservoir of heat is also known as heat bath. Okay. Now we consider two thermal systems. One with energy E minus epsilon and number of microstates E, number of microstates omega, which is function of the energy, and another system, thermal system, with energy epsilon and number of microstates, which is a function of the energy epsilon. This system 1 we can consider to be our, say, reservoir at some temperature T, and here system 2, this is the system which we would like to analyze. System to be analyzed. Okay. And we suppose that these two systems are isolated, okay, and somehow we let the system 2 to be in thermal contact with system number 1. If they are in thermal contact, then we can write the energy of the reservoir system plus the energy of our little system under consideration, sum to E. E is going to be fixed, is going to remain constant because the two systems are isolated. Okay. And here we also assume that epsilon is really tiny. It's very, very small compared to E, which is the total energy, which is fixed. Okay. We consider it to be really tiny such that the number of possible states with such energy can be obtained from a single microstate. Okay, so this can be assumed in some way. So it could be, one can say that this is an atomic behavior, right? So, for example, the lowest unit of energy possible is epsilon, and given an energy state of the system 2 to be epsilon, there is only one possible way of getting that energy epsilon. Okay, so we're going to assume this. So omega here is omega of system, here omega of reservoir, maybe I call it 1, omega of system, 2, call it 2 here. Okay. So building on our discussions from the previous video, I hope you can see that you can recall that the probability of the combined state to be such that the energy of system 2 is epsilon is going to be directly proportional to the number of microstates for the reservoir system. This is a function of E minus epsilon times the number of microstates of the system. So this is function of epsilon. Remember that since the two systems are isolated, then we have one variable, and that one variable we taken it to be this little energy of system 2, which is epsilon. If you remember what we've discussed earlier before in the previous video, we have two systems with energy E1 and the other with an energy E2, such that E1 plus E2 is E and E is fixed. Okay, so as the system is evolving, we have E1 and E2 changing, but there is one variable which we can use to describe the dynamics of the combined system, because we have this one constraint, E1 plus E2 equal to E. So here E1 can be energy of the reservoir, which is epsilon, which is E minus epsilon, and E2 is energy of the system. Okay? So I hope you can recall that this makes sense. And with the assumption that number of microstates for the system is 1, then we can write the probability of epsilon is going to be directly proportional to the number of microstates for the reservoir system. Okay. And our main target here is to use definition of temperature and then derive the probability P of E in terms of temperature, the Boltzmann constant, and number of states. So recall that 1 over kBT is the omega function of E by dE. Okay, so omega here, which is appearing for the probability, we can see that if there is a way to rearrange this formula, then we can derive let's say omega in terms of energy and temperature. Okay. And this can be done using Taylor series expansion. Okay, or one can see directly from this formula that if we integrate, then it's possible to find an expression for omega, so to say. Yeah. So since epsilon is really tiny compared to E, one can Taylor series expand let's say logarithm of omega. Here it's a function of E minus epsilon. Okay. Why logarithm of omega? The motivation is as stated. We have this formula, the definition of statistical definition of temperature here. That is what is going to be used. So we're going to make this Taylor series expansion. If you recall, let's put this as an aside, Taylor series expansion of f of x around some point A is something like this. You can write f of x to be f of a plus x minus a df by dx at x equal to a plus x minus a squared d squared f by dx squared at x equal to a, that way. So we can identify x with e minus epsilon this way. That is, we can identify the x with the e minus epsilon somehow. A can be identified to the fixed e, that is at x equal to a, what we have is actually x equal to e, so epsilon is let's say 0. We can identify f of x with logarithm of omega e minus epsilon. So we have log of omega e minus epsilon, Taylor series expansion, log of omega function of epsilon plus e minus epsilon minus e dA of log omega function of e minus epsilon by d of e minus epsilon at epsilon 0 plus higher order terms. So it can be seen that this is approximately log of epsilon, log of omega function of epsilon minus epsilon divided by kBt. So the definition of temperature, statistical definition of temperature is used. Okay, so we've used this formula to change this expression into that, and taking exponentials of both sides. So this is Taylor series expansion. Maybe I close the bracket here. So doing the Taylor series expansion, one can see that omega, a function of e minus epsilon, is approximately omega of e minus omega of e exponential minus epsilon divided by kBt. Okay, and therefore we can write the probability of epsilon to be directly proportional to exponential minus epsilon divided by kBt. This is what is called PE is called Boltzmann distribution. It is also called canonical distribution, sometimes also Boltzmann Factor. Yeah. And this probability, let me give it a different color here. The formula we have, so chop it out. That this is the probability distribution of how a system in thermal contact with a large reservoir is. So the probability, once the temperature is known, which is fixed, and then energy varies, the probability varies with energy in an exponential manner. So Boltzmann distribution is exponential. You can easily draw that. So this is PE. It's going to be an exponential distribution. Okay. An example where we can apply this is we can consider a system of gas. Okay. And for example, we can consider a single molecule within that system of gas. So the whole system of gas, other than the single particle we are considering, is going to be the reservoir. Let's say it's at some fixed temperature T. Okay. And the energy of the molecule, if we assume the gas is ideal gas, so it's a simple gas, it's a simplified gas where there are no structures for the molecules are point-like, and all the energy that we can associate to a single molecule is simply kinetic energy. Okay, so applying this Boltzmann distribution formula to a system of gas in this way is going to lead us to the next subject, which is going to be Maxwell-Boltzmann distribution. So if I go to the next page, I can talk about Maxwell-Boltzmann distribution. Okay. So you can write that the speed distribution, the speed distributions in an ideal gas can be obtained by using P function of E, which is the Boltzmann distribution, as we've seen above. So one can consider a molecule, a single molecule, for example, as this is a small system, one may say. The single molecule is existing in a gas, a container of gas. So in a gas at a fixed temperature T. Okay. So the whole gas can be considered as a reservoir. So this kind of sort of connects to the discussions we've just had. So here, for example, epsilon is going to be energy of molecule, and if the molecule is an ideal gas, we can take that to be purely kinetic energy, half mv squared, where v is the absolute value of the vector v velocity, and so v vector v is the molecular velocity, so maybe vx, vy, vz, the molecular velocity vector. Okay. So we can define a velocity distribution function such that, for example, if we take a single component of velocity of a molecule, then I can define g function of vx. So vx is this the x component of the velocity of a molecule. gvx times dvx is going to be the probability. This is probability of finding a molecule having how can I call this? So having, let's say, x component of the velocity, x velocity within the range Vx and Vx plus dVx. So this is a probability density function or probability distribution from which we can get the probability of finding a molecule with Vx in the range Vx to Vx plus dVx. Applying Boltzmann distribution then implies that g of v of x is the probability. So this g is like the p of e here. So this is going to be directly proportional to e to the minus mvx squared divided by 2 kb times t. So all that we've done is that we've used this formula in the spatial case where epsilon is the kinetic energy of a single molecule in a given direction, right? So we consider a one-dimensional molecule. Let's say it can only move in the x direction. Okay. G v of x can be normalized. You can use the formulas by requiring that all sum of these probabilities goes to 1. Okay. And that is, if I put what g of x g of v of x is, I'm going to get minus integration minus infinity to infinity e to minus m vx squared divided by 2 kbt dv of x. This is going to be equal to pi divided by m divided by 2 kbt square root. Yeah. And from there, this is using the integration formula I0, which I have given in a previous video. I think the third video, where we talked about probability distributions and integration formulas. You can integrate this to that, and that implies that g v of x, which is normalized, is going to be equal to m divided by 2 pi kbt all at home in a square root e to the minus m vx squared divided by 2 kbt. So all we've done is to apply Boltzmann distribution for the case of a molecule of a gas, where the energy of the molecule is the kinetic energy, and here we have considered a one-dimensional molecule, so we're just considering Vx. From there we can find the probability density, G function of x. Okay, and hopefully you can see that this is actually a Boltzmann kind of distribution. Okay, it is quadratic in the exponent. So maybe we can just write a tiny distribution somewhere here if possible. I'll do it here. So it's going to be, this is a very rough Gaussian distribution. Hopefully we can see v of x, and this is how g v of x is. Yeah, and this is centered at 0 or something. Right. So what can apply, can use this probability distribution? So we have a probability distribution. What are those probability distributions good for? You can use them to compute averages, just like we've discussed earlier in an earlier video. So this formula can be used to compute the average velocity, the average absolute velocity, the average of the velocity squared. This is all easily done because you have the distribution, and also you have these various formulas which we have given earlier, so you can use them to do integrations, right? For example, using the integration formulas, see video 3 of the kinetic theory of gas series. So there is this formula as we've discussed there, using I0, I1, I2, I3 and all that. You can get the following results, that the average velocity in the x direction is defined as the integration from -infinity to infinity of v of x, what we want to find the average of, times the probability density function, which we know what it is. Okay, so you can show that this is going to be 0, but the absolute value, the average of the absolute value, is not going to be 0. You can show that this is going to be equal to 2 kbt divided by pi m. So if you want to see this, how this is done, I really encourage you to take a look at video 3 if you haven't done that already. Okay. The average of Vx squared is going to be integration from -infinity to infinity of Vx squared times v of x times g of v of x dv of x, and this is going to be kbt divided by m. Okay. Building on this one-dimensional example, we can see that the probability of finding a molecule with velocity, let's say v, with velocities between, so this is three-dimensional velocity I'm talking about here, between vx, vy, vz, and vx plus dvx vy plus dvy vz plus dvz. And recall that velocity is a continuous variable. Treating it as a continuous random variable, velocity of molecule in a gas, then the probability of finding a molecule with this specification can be obtained using, you just multiply the probabilities. So it's going to be g v of x, dv of x, g v of y, dv of y, g v of z, d v of z. And this is going to be proportional to, I hope you can see, so just fixing the formula for g, we know what the formula of g is, and that is going to be, if we put the constant aside, minus m divided by 2 kbt. If we factor this out, we're going to get vx squared plus vy squared plus vz squared, and this is equal to e to the minus mv squared divided by 2 kbt. So yeah, we have shouldn't forget the factors. Let's say d vx dvy dvz times dvx dvy dvz. Okay, so here it's going to depend on really the magnitude of the velocity squared. Okay. If instead of velocity, if we consider the speed of a molecule, right? Then what's going to happen is that for an ideal gas, then the probability that a molecule is going to have speed, okay, speed, let's say between v, so how should I write this? Speed, let's say in v and v plus dv, right? This probability one can compute as usual to be equal to some probability distribution, probability density function, let's call it f of v here, times dv, so which is the volume element, right? Remember, this is probability density times volume, so this is going to give you the probability. Now the probability density f actually is going to be f of v when we use Boltzmann distribution, right? F of v is going to be proportional, okay? Or if I just, because if I keep f of v for later, then I can write this probability density here, okay? This is going to be proportional to e to the minus mv squared divided by 2 kBt, using Boltzmann distribution, just like what we have computed here, right? But the volume element, on the other side, we need to be careful for that. For the volume, so I write the volume in speed space corresponding to speeds of the molecule between v and v plus dv. This is going to be equal to surface area. So speed is something positive, so 0, and it takes values between 0 to infinity. So one can consider like an arrow to represent the speed, and let's say I have an arrow here, right? It can take values from 0 to whatever to infinity, and this arrow I can consider it to cook out a sphere. So there are different possible ways. If I vary v, it can like so in 3 dimensions, it's going to make a sphere, locus of sphere, if I vary it. And so the volume is going to be surface area times dv. Okay, so I have v, and then like increasing it a bit with dv. Okay, so this volume element is actually going to be equal to 4 pi v squared times dv. So 4 pi v squared is going to be the surface area of a sphere, which I can build out of this. So roughly speaking, this is not really a sphere, but approximately one can approximate. So let's make it that way. Let's say, right? So instead of this one-dimensional cycle, it's going to be a sphere. So the volume element with respect to dv is the surface area of the sphere times this elemental increment in the speed dv, right? So to get the probability of having like a molecule with speed between v and v plus dv, what I'm going to do is that, let's go to the next page. So probability speed of molecule is between v and v plus dv. This is going to be equal to so this is going to be equal to the Boltzmann factor, E minus mv squared. Let me write that again. V squared divided by 2 kBt times 4 pi v squared dv. Okay. Therefore, actually, our probability density for the velocity times dv is going to be that, right? So we're going to get v squared e to the minus m v squared all over 2 kBt dv. Okay. And yeah, that's it. So concerning speed of a molecule, you can see that the probability density f of v is proportional to v squared e to the minus m v squared divided by 2 kBt. And one can normalize f of v like we've done before. So f of v can be normalized in this way. We require that integration from minus infinity, so since speed is varying from 0, so we integrate from 0 to infinity f of v dv. We require this to be equal to 1, and doing the integration using the formula again. So this is again from 0 to infinity of v squared e to the minus m v squared divided by 2 kBt dv. this is going to be 1 divided by 4 pi squared divide by m by 2 kbt. This is to the cubed, and you have square root here. So you have to be careful when you use, so this, you can get this using I2 formula. I2 is given already in this video number 2. But when using I2, I think I2 was an integration from minus infinity to infinity, but here we're doing integration from 0 to infinity, and so you have to be careful with the factors here. So using this result, one can see that, so f of v dv is going to be equal to, one can write it as 4 divided by square root of pi m divided by 2 kbt to power 3 by 2 v squared e to the minus m v squared divided by 2 kbt times dv. So here f of v is the Maxwell-Boltzmann Boltzmann speed distribution of a molecule. Okay, and it's a bit different compared to Gaussian. It's not a Gaussian because we have 0, roughly something like that. Hopefully we're going to have a session where we can play a bit with some codes, hopefully to see, to plot these functions, and also maybe how to sample from those distributions. But here, roughly speaking, there is a maximum value, and it starts from 0. It connects to 0, and v goes to whatever, it goes to infinity. Yeah. You can compute the maximum value Vx by differentiating. So if you do df of v by dv equal to 0, you can get that the maximum speed of molecule is actually this 2 kbt divided by m. So it's proportional to the square root of the temperature. Yeah. So similarly, now we have probability distribution, probability density function concerning like the possible values, the speed a molecule can take, and using that again you can compute averages like we've done for the one-dimensional molecule case. So I'll just write that before to round out. Knowing f of v is the Maxwell-Boltzmann distribution, one can compute the following averages using the integration formulas using the integration formulas which I have given like before. And so this is here you can see average of V is integration from 0 to infinity V f of V dV which is equal to 8 kBT divided by pi times m. Square root. And the average of V squared, so you can use this to compute the dispersion, is integration from 0 V squared. We know f of V, so we can do the integration, and the answer is going to be 3 kBT divided by m. And so, and the root, the same for the root mean square, root mean square written RMS speed V RMS will be square root of the mean of V squared. So this is going to be 3 kBT divided by m square root. And also one can see from the average of V squared that the average kinetic energy is 1/2 m average of V squared. So this is going to be 1/2 m times 3 kBT divided by m. So this is going to be 3/2 kBT. So this is a very nice result. You can see that the kinetic energy is directly proportional to the temperature. Yeah. So we can see that the modeling, the kinetic theory is actually giving some results here. You can compute the average energy for a gas, right? And I think that's it for now. But one can also do some comparisons. You can compare these quantities, the average of the velocity, the V maximum speed, the average of the speed, the maximum of the speed, and the V root mean square value. And so maybe I'll just give that here. We can see that average of V divided by square root of kBT m. This is square root of 8/pi, and same thing for V max divided by kBT/m square root. This is going to be square root of 2. And V RMS divided by square root of kBT/m. This is going to be square root of 3. So one can see that VRMS is less than the average of V. This is less than V max. Okay. Since square root of 2 is less than 8 divided by pi is less than square root of 3. This is a very nice result, which you can also check by plotting the different quantities here computed. I think that's it for today. I hope you find this useful, and see you next time. Goodbye for now.